Hello, and welcome to Chapter 3 of the OpenStax Psychology textbook. My name is Matthew Poole, and I'm an instructor of psychology at Northeast State Community College. And today we're going to be going over biopsychology. So, what is biopsychology? Biology includes both biology as well as psychology and how they intermingle together. So, particularly, this field of study looks at your genetics and how they influence you, not just behaviorally, but also physiologically. As well, it looks at the structure and the function of the nervous system. So, the field of study that particularly focuses on the study of the nervous system is what's known as neuroscience. And that's becoming a more popular major at a lot of schools. And so, how biopsychology differs from that is it includes other features such as how, again, your genes, what you get from your parents influences you, along with how the nervous system interacts with your endocrine system. All right. Now, there are a couple basic cells of your nervous system that I want you to focus on. If you're in my class, this will be for a test. These are neurons as well as glial cells. So, neurons, to give a definition to, though, these are responsible for receiving, interpreting, and then sending electrochemicals on to the rest of your brain and other parts of the nervous system. And there are some structures that I really need you to hyper focus on. Right over here, you can hopefully see my cursor. And the structure that I want to begin with are these tree branch like structures that are known as dendrites. They are responsible for receiving information, and then they will send that on across the soma or the cell body, not this purple like structure. That's going to be your nucleus. And then it's sent down the axon and will end up at the terminal buttons. Now, this protective layer over here that looks a little translucent is what's known as the myelin sheath. And this is just what allows the information to travel across the neuron a lot more smoothly. Okay. Now, your synapse, all right, is what you're looking at here. Up top is going to be your presynaptic cell. Below is your postsynaptic cell. And this is like the end of the terminal buttons and the beginning of your dendrites. So we all have natural neurotransmitters, and I'll define what a neurotransmitter here in a second, but we all have natural ones like serotonin, dopamine, norepinephrine, things like that we naturally release. And whenever we release them for an action potential to occur, they will bind to their applicable receptors. All right. And so once an action potential occurs, any excess neurotransmitter is then going to be reabsorbed within the presynaptic cell. Once again, this little area right here in between, it's like a super close, like the highest game or the best game of I'm not touching you ever. But it's hyper focused in right here to show you that there is some sort of synaptic cleft. Okay. Moving on. So whenever it comes to reuptake, like I said, I simply mean reabsorption. And there are a lot of drugs that you can take that prevent the reabsorption of particular neurotransmitters so they can continue binding to their applicable receptor and then continue an action potential. A common, which that medication is strictly focused on assisting people with mental difficulties, is an SSRI. An SSRI stands for selective serotonin reuptake inhibitor. And whenever you break it down, it's a lot simpler than what it sounds. We obviously know the neurotransmitter that it's acting on is serotonin. So that's selective serotonin reuptake, which means reabsorption. And then lastly, inhibitor. So it inhibits the reabsorption of that serotonin back into the presynaptic cell. So there's more available within the synaptic cleft, so it can continue binding to its receptor. Now, commonly people are prescribed an SSRI for anxiety as well as depression. So if it prevents that reabsorption of serotonin, then it has more here that's available, so it can continue over and over again, causing an action potential, thus alleviating mental difficulties such as anxiety and depression. Now, I've said the word neurotransmitter a lot, but to give a definition to it, these are the chemical messengers of the nervous system. And there's a biological perspective when it comes to these neurotransmitters. And if there's a sort of imbalance with them, then that can cause certain mental difficulties. For example, schizophrenia, there's a hypothesis that if there's too little or too much dopamine, then that can either cause the positive or negative symptoms of schizophrenia. Now, some other natural neurotransmitters that I've mentioned dopamine that's involved in reward, craving, learning, and addiction. We'll talk a little bit more about it in this chapter as well as others. Norepinephrine, which stimulates the nervous system largely, but more so it helps with alertness as well as serotonin, mood, and sleep. Now, when particular psychotropic medications, to give a definition to it, as I've already mentioned, they help treat these mental difficulties by restoring neurotransmitter balance. Now, there are two overall categories of drugs in general. These are agonists as well as antagonists. This is something that's going to be important to know for a test. So, drugs that are considered agonists, they promote, mimic, or strengthen neurotransmitter activity, such as SSRIs, as well as a common drug that we take every day. And I say that word drug, and it may have a harsh connotation to it, but there are mild stimulants that we take, such as we drink coffee every day. So we're getting that caffeine from it. And so it promotes dopamine activity. That's why we continue coming back to caffeine among other stimulants, because it acts on that very neurotransmitter that says, hey, whenever you're presented with this in the future, engage with this very person, place, or thing. Okay. Caffeine also works as an antagonist. Antagonist is a drug that blocks or impedes neurotransmitter activity. So how caffeine works is it's an adenosine antagonist. Adenosine is the neurotransmitter that builds up throughout the day and tells you that you're tired. Whenever we first wake up, we're obviously pretty groggy. So whenever we consume caffeine and through energy drinks or other forms, such as your basic cup of coffee, it will block adenosine from binding to its applicable receptor. So effectively just trying to tell yourself that you're not tired. But caffeine also stimulates your adrenal gland. So that's why we have that alertness, and why some people, if they're sensitive to caffeine or if they drink too much of it, they'll begin to experience adverse effects such as anxiety and things of that nature. Okay. So agonist, which is important to know for a test, a drug that mimics or strengthens neurotransmitter activity, and antagonist works by blocking particular neurotransmitter activity. All right. Now, whenever it comes to the parts of the nervous system, let's break this down a little bit more in depth. You've got two overall categories known as the central nervous system, which strictly involves your brain as well as your spinal cord. And then you have your peripheral nervous system. So that's why whenever individuals have damage to their spinal cord, that information cannot be sent to the rest of your body. The peripheral nervous system includes all your nerves, which helps you move and do other motor activity. Okay. All right. So when it comes to your peripheral nervous system, again, that's strictly focusing on your nerves. We break that down even further into the somatic nervous system as well as the autonomic nervous system. I'm going to skip ahead to the next slide because this just gives a better visual representation. So we've already established the central nervous system as well as the PNS, and then we've got the somatic nervous system and the autonomic nervous system. So the somatic nervous system includes all that voluntary control, such as if moving your arm, moving your leg, walking, running, etc., things that you can voluntarily control. When it comes to your autonomic nervous system, these are things that, again, you can think of autonomic like automatic. You don't have to think of it. You don't have to tell your stomach to digest. You don't have to you don't have to tell your heart to beat, things like that. It just does it automatically. Now, under the autonomic nervous system, we break it down even further into the sympathetic versus the parasympathetic nervous system. And this is important to know for a test. Whenever we experience or we perceive a threat, our sympathetic nervous system will kick on. That's what's known as our fight or flight or freeze response. So we either fight the situation, run from it, or we may be so petrified that we freeze altogether. Once that perceived threat is taken care of, we then will see our parasympathetic nervous system come in and calm us down. It basically the rest and restore side of the autonomic nervous system. A quick example of this to show how both quickly interact is that, let's say that you're scrolling through your phone or you get an email or whatever the case is, and somebody has sent you or you stumble across a video that is a jump scare, right? The car is moving through up the road. It's a nice, peaceful image or video, I should say. And then out of nowhere, like this ugly, terrifying demon face that's screaming at you. Automatically, your sympathetic nervous system will kick in because it perceives a threat. And so that's why you get that sinking feeling in your stomach. You get like frightened, all that. But almost as soon as that sympathetic nervous system kicks in, and then you understand that the perceived threat is no longer a perceived threat, it was just a jump scare, your sympathetic nervous system will come in automatically to come and calm you down. All right. Now, when it comes to your brain specifically, you have two hemispheres, right? And so there's this little strip of tissue that we'll talk about here in just a second that connects the two and allows them to communicate. However, there is a concept that I want to go over known as lateralization. This is the idea that, of course, each hemisphere has specific functions. Another example for this would be like if whenever you have things like, such as in your left hemisphere, for most people, you have what's known as Broca's area in your frontal lobe on the left side. And so that is what's responsible for speech production. Okay. You also have Wernicke's area for most people there in that left hemisphere where it's responsible for speech comprehension. On top of that, let's say that an individual experiences a stroke. Unfortunately, that's a common thing that happens. And so if they have a stroke specifically in their left hemisphere and there's damage to Broca's area as well as Wernicke's area, then individuals will experience difficulty with speech production and or speech comprehension. So understanding what people are saying and actually being able to say what you are viewing or just communicating in general. Next is, again, that corpus callosum. That's that strip of tissue that connects the two hemispheres that allows them to communicate. So there have been some studies, and there's also been things in medicine where they have taken out that corpus callosum for individuals who have Parkinson's disease to alleviate seizures. The difficulty, though, with removing that corpus callosum is that, again, where language is largely processed in the left hemisphere, if I put something in your left visual field, that information goes to your right hemisphere for processing. And if there's a removal of that strip that communicates the two hemispheres together, then it's going to be really difficult, if not impossible, to say what that image is. But then as soon as you move it into your right visual field, that goes to the left hemisphere where speech production as well as comprehension is largely processed. So that's why every single structure in your brain is there for a reason, and it is super important. That's why minimizing damage as much as possible is, of course, ideal. But we see all sorts of cases where people who play sports, and of course, I'm the biggest fan of football that there is. It's my favorite sport to watch, but I can't help but think whenever I see people take these huge hits, especially linemen who are constantly hitting their frontal lobe, as well as those who take really big hits where it knocks them unconscious and things like that momentarily. I can't help but think what damage they accrue that may not be an immediate experience, but long term can cause difficulty because we see and continue to hear things about CTE. For those that are sports fans, you probably heard that phrase pretty frequently. But yes, behavioral difficulties can occur after you retire from your respective sport. Now, there are three categories of the brain overall: the midbrain, the forebrain, and the hindbrain. And we're going to dive into each one and specifically look at the lobes of the brain, the four lobes of them. Some other structures that we'll go over today include the cerebral cortex, the thalamus, the hypothalamus, the pituitary gland, as well as the limbic system. Okay. All right. So whenever it comes to the cerebral cortex, this is just overall the surface of the brain that's associated with our highest mental capabilities, such as consciousness, thought, emotion, reasoning, language, as well as memory. And the four lobes of the brain include the frontal lobe, the parietal lobe, the occipital lobe, as well as the temporal lobe. So one of the ways that you can remember this is I like to just do the acronym FPOT. It helps me remember it. Maybe it'll help you because drugs are bad, right? FPOT: frontal, parietal, occipital, and temporal. And we'll break each one. Now, when it comes to the frontal lobe, this is hugely important for higher level processing. So you have structures known as the motor cortex, the prefrontal cortex, and again, like I've already mentioned, Broca's area. All right. So whenever it comes to the motor cortex, this is involved in planning as well as coordinating movement. As you'll notice as we go throughout, different areas of the brain can serve the same similar functions too. So the motor cortex involved in coordinating movement, as well as your cerebellum, which is like a mini brain, but we'll talk about that whenever we get there. Prefrontal cortex. This is responsible for higher level cognitive functioning. It's really important for decision making, problem solving, as well as judgments. Obviously, when there's damage to this area, individuals can expect there to be difficulties with impulsivity. All right. And one of the ideas behind ADHD, particularly, is that there is difficulty with that frontal lobe and maybe even prefrontal cortex specifically, because we notice for individuals who have ADHD, there's an impulsivity difficulty as well as decision making difficulty. As already mentioned, Broca's area in the frontal lobe for most people is in the left hemisphere, is involved for speech production. So actually being able to say particular things. And there is a story known as Phineas with the individual named Phineas Gage. Unfortunately, Phineas Gage was the individual to show us that one of the earlier figures to show us whenever there's damage to that particular area of the brain, there are difficulties to follow. What happened to Phineas Gage is he had a tamping iron or an iron rod go underneath his cheek and up through his frontal lobe, and it severed that frontal lobe from his limbic system. And the reason that this is important, and maybe this is up ahead here, there we go, is the limbic system is really important for emotion processing. After his accident, he did recover physically, but he had difficulty with his mental processing and emotion processing. So he had emotions just going through with reckless abandon because that limbic system was severed from his filtration system, otherwise known as the frontal lobe, and specifically that prefrontal cortex. Okay. But more on that here in just a second. I don't want to get too ahead of myself. So now we're going to move toward the parietal lobe. The parietal lobe is on the top of your head. Okay. So whenever it comes to the parietal lobe, you can think of this lobe as the sensory lobe because it processes a lot of your senses, except for one in particular. And we'll get to that here in just a little bit, but it's really important for touch, temperature, as well as pain. And you can see that as illustrated by figure 320. Moving on. So frontal lobe, really important for high level processing, parietal, your senses. The temporal lobe, this one's a little bit easier to remember because it's near, you can think it near the temple. I'm circulating it here with my mouse. And the temporal lobe, again, it's not just for speech comprehension, understanding what people are saying, but the auditory cortex. So it's overall in general really important for speech comprehension. But for a test, and this is something that you would probably be tested on, understanding the difference between Broca's and Wernicke's is really important. Broca's is actually being able to say things. Wernicke's is understanding what people are saying. So when there's damage to that, you can expect there to be difficulty on that end. When it comes to the occipital lobe, this is at the very back of your brain. The occipital lobe is hugely crucial for vision, okay? Although our eyes are at the very front of and they're underneath the frontal lobe and at the front of our face, the overall processing is done at the very back with the occipital lobe, the final processing. Information that's in the left visual field goes to the right hemisphere, and the right visual field will go to the left hemisphere. All right. On top of that, we have what's known as the thalamus. This is ultimately the relay center for the brain where it helps with most senses, but it excludes smell. Okay. So that is likely going to be processed up in the parietal lobe. But the thalamus is hugely important for relaying information specifically related to your senses. Okay. Moving forward, again, revisiting the limbic system, we have what's known as the amygdala, the hippocampus, as well as the hypothalamus. When it comes to your amygdala is one of the processes that's involved in processing emotions in general, but specifically fear. So whenever you have that fight or flight response kick on, your amygdala is involved in that. So when you perceive a threat, your amygdala is involved in processing that fear, but emotions in general as well. Now, when it comes to the hippocampus is hugely crucial for memory as well as learning, and in particular, spatial memory. So again, amygdala involved in processing emotions, hippocampus involved in processing memories, and then finally, your hypothalamus is important for regulating things like your body temperature, your appetite, and your blood pressure. So think of the hypothalamus Hypo equals homeo. Hypothalamus is involved in making sure you're at homeostasis, or making sure that everything is at an even state overall. Next, the next category we're going over is the midbrain. So the midbrain involves really important structures for dopamine production. Things such as the substantia nigra as well as the VTA, really important for dopamine. All right. Now, another structure in the midbrain that's really important is reticular formation, crucial for regulating the sleep wake cycle. And whenever we get into later chapters talking about jet lag and things like that, this reticular formation structure will come back up. All right. Moving forward, we got the hindbrain. And the hindbrain is including the cerebellum as well as the pons and the medulla. So overall, it is considered the brainstem. So the hindbrain is the brainstem, connects the brain to your spinal cord. So your cerebellum is crucial for things such as motor coordination as well as memory, specifically focusing on that muscle memory. And although it's not in the muscle, it's in the brain. You all already know that, but we consider it muscle memory for lack of better terms. Okay. We all saw, at least most of us, I don't know what year you're watching this or what semester you're watching this, but there is a football player named Tua Tagovailoa. And you can either YouTube this or Google it down the road, but he took a massive hit in a couple of games this past season in 2022. And whenever he fell down, he was thrusted right down onto the back of his brain where his hindbrain is. And you'll notice that he gets up. Of course, he suffered a concussion, but he specifically struggles with motor coordination right after, has difficulty with balance, and ultimately just falls right back to the ground because he fell right back on his hindbrain. Okay. Moving on. We're going to finish out talking about some different brain imaging. So we're going to involve techniques that involve radiation, magnetic fields, as well as electrical activity. So your most basic brain scan is going to be what's known as a CT scan. It just gives us an X-ray of the brain, and it's mainly used for showing tumors that are in the brain or if they've grown after some time, things like that. So it's just your basic X-ray to see and to look at your brain overall. It doesn't give us much more information past that, though. That's why PET scans are really good to have, because you're either ingest or injected with a mild radioactive substance, and it helps in monitoring changes in blood flow through different regions of the brain. So it can help us see which parts of the brain are more active than not, or just in general to see if you may have a hypersensitivity or a lack of sensitivity when you're shown certain images or videos, etc., things like that. Now, when it comes to MRI and fMRI, we're using magnetic fields to produce an image of the tissue. Okay. And so we can see through an fMRI the changes in metabolic activity over time. So it's really important to have an MRI and fMRI for giving us this particular information to see that metabolic activity. We also have what's known as an EEG. These are commonly used for sleep studies to see activity as well as brainwaves, things like that, track that. You'll see individuals wear these sorts of caps like this young boy is right here to see the amplitude and the frequency of brainwave activity. And again, commonly used for sleep studies. Lastly, we're going to go over the endocrine system, some different structures in it. But the endocrine system, to give a definition to, is the series of glands that produce hormones that regulate normal bodily functions. Okay, so the hypothalamus links the nervous system and the endocrine system by controlling what's known as your pituitary gland. And so that pituitary gland serves as your master gland that really ultimately controls the rest of the other glands and the secretions of them. A very important portion or structure of the endocrine system is known as your thyroid. It secretes thyroxine, which regulates growth, metabolism, as well as appetite. And so if people have difficulty with their thyroid, it can cause a whole host of difficulties. It can impact your anxiety. It can impact, of course, your growth, specifically your metabolism. If it's underactive, individuals may experience a weight gain as a result of an underactive thyroid, as well as appetite can be impacted. Your adrenal gland, as I've mentioned, secretes hormones involved in the stress response. So whenever you consume caffeine and all of that, you'll notice that these hormones last a little bit longer. And that's the difference between a hormone versus a neurotransmitter, is that hormones last a little bit longer, or a good bit longer, I should say, because when you experience a stressful event, if you still feel a little bit jittery or anxious afterward, you can thank your adrenal gland for making you feel a little bit more stressed for a longer period of time. And lastly, we have the pancreas, which is crucial for regulating blood sugar. So, for those individuals who unfortunately have diabetes, they have difficulty with their pancreas in secreting the correct amount of hormones that regulate their blood sugar. All right. So, that's going to complete chapter 3 of the OpenStax Psychology textbook. And I'll see you in the next one for chapter 4.